Greetings, statistics scholars, and welcome to this next in our series of videos on Chapter 2 from your text, dealing with ways of describing data. In this section, which focuses in on section 2.3, we're going to be talking about looking at measures of spread for a quantitative variable. To start off with, let's suppose that we have a waitress named Beth, and she has a list of her tip amounts that she's received each day over the last quarter, and she takes a simple random sample of those tip amounts. And she takes a simple random sample of size 8, and you can see the results in the column on the left. Now, on some of those days, she had a great day, making $36.80, for example, on the last day in the sample. The first day of the sample, $30.10 was her poorest day. Most of the days she did somewhere around $32 or $33 in tips for that day. Now, if we go to StatKey or use some other technology, we can get some summary statistics from this sample. And there we have them there, a sample of size 8, and you can see, indeed, for our measures of center, we're getting an average tip amount of $32.50 in total tips per day, with a median amount of $32.80 per day. Now, when we look at those summary statistics, in addition to the measures of center, like the mean and the median, we see some other values there, like the standard deviation and some things labeled Q1 and Q3. In this video, we're going to take a look at measures of spread. And we'll ask the question, what are some different ways that we could use to describe how spread out this data set or any data set is? I'm going to begin by looking at perhaps the simplest and most straightforward way to talk about the amount of spread in a data set. And that's the difference between the maximum and the minimum values for the data set. We call that difference the range of the variable. The range is the maximum minus the minimum. So for Beth's data set of daily tip amounts, the range would be the difference between $36.80, which was her maximum, and $30.10, which was her minimum. That difference that we get by subtracting those, $6.70, is called the range of the data set. And range can be one way of measuring how spread out the data is. We're going to look at some other methods as well. So let's proceed onward. We're going to talk in these next few slides about some things called percentiles and quartiles. Now, if we take those 8 daily tip amounts for Beth and arrange them in increasing order, we can see that list there. We can use that to find the median value. There's the lowest 50% or lowest 4 values. And there on the right, we have the upper 50%. So to find the median, we know we're going to take, in this case, since we have an even number of values, the average of the 2 middlemost data points. The median value here is the average of $32.70 and $32.90, and that's going to give us a median value of $32.80. That median has a couple of other names that we can refer to it by. The median is sometimes also known as the 50th percentile, or P sub 50, since it has 50% of the data values below it. Another name that we sometimes use for the median is Q2, the second quartile, because what is 50%? Well, it's 1/2 or 2/4. So the median, or P50, the 50th percentile, is also can be referred to as Q2, or the second quartile, because it has 2/4 of the data values less than it. Continuing in that fashion, Let's look a little bit more closely at the lower 50% and the upper 50% of this data set. Now, the values below the median, the four values below 32.80, they have a median themselves. It would be the average of $33.30 and $30.40. The median value for that lower half of the data would be $30.35. Now, how could we refer to that median of the lower 50%? Well, we see that that value, $30.35, has exactly 2 out of the 8 values in the data set below it. That's 1/4, or 25%. So because $30.35, the median of the lower half of the data, has 1/4, or 25% of the data values below it, one name that we give to that number, 30.35, is we call it the first quartile, because it has 1/4 of all the data points below it. Now, since 1/4 is 25%, we can also refer to that value as the 25th percentile, P sub 25. So Q1, the first quartile, means the 25th percentile, and here, for Beth's tip data set, that would be $30.35. We can do that same idea with the upper 50% as well. Let's take a look at the median of the upper 50%. When we take a look at the median of the upper 50% of the data, we see that the average of the two middlemost data points there is $33.40. What name would we call that by? Well, we see that it's got 2 values above it and 6 values below it. 6 values below it is 6/8, or 3/4. Because 33.4 has 3/4, or 75% of the data values below it, we'll refer to that as the third quartile, or as the 75th percentile. So these are two additional numbers that are usually very helpful to know for a data set, Q1 and Q3, the first quartile and the third quartile. Now, we introduced the notion of percentiles there. In general, the nth percentile for a data set, which we label as P sub n, is a number that has n% of the variable's data below it. So for example, suppose that we have a different data set. This isn't Beth's data set, but suppose we have a data set of chemistry test scores from Professor Lancelot's section. And here are the 10 scores that were achieved by the students, ranging from 46 as the minimum up to 98 for the maximum. And suppose we wanted to talk about some percentiles. If we ask what is the 30th percentile for this data set, we would say that the 30th percentile for this data set is the number 72. Why? Well, because 72, which is the average of 70 and 74, the third highest and the fourth highest data values, that number has exactly 3 out of 10 data values below it. It has 30% of the data values below it. And so hence we refer to it as the 30th percentile. What if instead of finding the 30th percentile, we wanted to know the 90th percentile? Well, that would be the average of the 9th highest and the 10th highest data values. It's going to be the average of the student who scored 92 and the student who scored 98. That average of 92 and 98 is going to be 95. So we will say that P sub 90, the 90th percentile, is 95 because it's got 9 out of the 10 data values below it, 90%. So in general, that's our notion of what we mean by a percentile. And the most important percentiles that we usually talk about are the 25th, the 50th, and the 75th, which we call Q1, Q2, and Q3, the three quartiles of the data set. When we think about those quartiles, they can give us another measure of spread for a data set, something that we call the interquartile range. The interquartile range, or IQR, is defined to be the difference between the third quartile and the first quartile of a data set. So let's think again about Beth's tip data set, looking at those 8 randomly selected days and the total tips she received on those days. We remember that we had just noted that Q3, the third quartile, was $33.40, and Q1, the first quartile, was $30.35. The difference between those two quartiles is going to be what we call the interquartile range. So for our tip variable, IQR is Q3 minus Q1, 33.40 minus 30.35. That's going to be $3.05. That is the IQR, or interquartile range, for the data set. The interquartile range measures how spread out the middlemost 50% of the data is. Remember that there's 25% of the data below Q1, 25% of the data above Q3. So that measure of spread tells us how spread out the middle 50% of the data is. Now, one very nice feature about the interquartile range is that it is not influenced by the effect of outliers like the range is. If you had one very high or one very low data value, that can make a very big change in the range of the data set, since the range uses the maximum and the minimum. But having one or two very high or very low values won't change the values in the middle of the data set. And so for that reason, we say that the IQR is resistant to the effects of outliers. And that can make it a very durable and useful measure of spread for a data set, because it can't be influenced or changed by one or two unusually high or low values in the data set. So far we've taken a look at the range, the difference between the maximum and the minimum, in the interquartile range, the difference between Q3 and Q1, as two important measures of spread for a data set. But we have one other measure of spread that's really significant that section 2.3 talks about. We'll be getting to that shortly. When we take the quartiles of a data set, for any quantitative variable that we're describing, we can give what we call the 5-number summary for the data set. That's a list of numbers that includes the maximum value, the first quartile, the median, the third quartile, and the maximum value of the variable. Those 5 values put together we refer to as the 5-number summary. In a way, you can think about the 5-number summary as the 5 data values that kind of bookend the 4 quarters of the data. For example, there's 25% of the data between the minimum and the first quartile. The next 25% of the data is between the first quartile and the median. The third quarter of the data is between the median and the third quartile. And the highest 25% is between the third quartile and the maximum. So the 5-number summary are essentially 5 values that kind of bracket each of the 4 quarters of the data in the data set. Now, when we do summary statistics, for example, with StatKey, we're often going to see those 5 numbers in the 5-number summary listed in a row. Here we see them here: minimum, Q1, median, Q3, and maximum. And on other technologies, for example, the Texas Instruments 83 or 84 calculator, you'll also notice that those 5 values tend to be listed in order. In this particular case, we would say that the 5-number summary for the tip data set consists of the numbers 30.1, the minimum, 30.35, the first quartile, 32.8, the median, 33.4, the third quartile, and 36.8, the maximum. The 5-number summary. We want to remember that the 5-number summary consists of the minimum, the 3 quartiles, and the maximum of the data set. And we indicated earlier that we were going to talk about another important measure of spread beside the interquartile range and the range. And that is something very important that we refer to as the standard deviation of a variable. It is yet another important measure of how spread out a variable's values are. When we take a look at summary statistics like these ones here that we've had for Beth's tip data set, we'll always see the standard deviation listed. Here we see the standard deviation for this data set is 2.247 approximately. But where did that number come from, and what does it signify? The standard deviation is a measure of how far on average a variable's values tend to deviate from the mean value of the variable. Let's say that again. The standard deviation is a measure of how far on average a variable's values tend to deviate from the mean value of the variable. Let's take a closer look again at Beth's tip data set here. Here's a dot plot of those 8 values, and you can see that I've put a little bar there to indicate where the mean value, $32.50, is. You can see that some of the days Beth had tip amounts that were below average, and on 5 of the days she had tip values that were a little or a lot above average. Now, for every one of those days, we can talk about how far did her data value for that day deviate from $32.50. Some days she had tip amounts that were below average, that were below that mean value. There's one of them. On one of the days, we recall she had $30.40 in tips. Now we can ask, how far does that deviate from the mean? Well, it's below the average, isn't it? If we look at the distance from the mean to that point, $30.40 minus $32.50 gives a difference of negative $2.10. For that particular data value, we have a deviation of negative $2.1. Then again, Beth also had a number of days, 5 of them in fact, in which her tip amounts actually exceeded the average. If we take a look at her very biggest day of tips, that day when she had $36.80 in tips, that particular data value would have a deviation that is $36.80 minus $32.50, or a deviation of positive $4.30. So in general, there's going to be some data points that are going to have negative deviations from the mean, and some data points that are going to have positive deviations from the mean. Now, how can we use those deviations to come up with a measure of how far on average the values are away from the mean? Let's take a closer look at how this is done to explain where we get that number of 2.247 from for the standard deviation. Here's our dot plot again to remind us of our data values. Now here's the list of all of those 8 data values. And what I've done beside each of them is I've computed out the deviation from the mean. You'll see the 2 deviations that we talked about on the previous slide for the $30.40 and the $36.80. But we can see now that we have the deviations for every single data value. So that first day when she made $30.10 in tips, that was $2.40 below the average. The day when she made $32.70, well, that was 0.2 or 20 cents above the average. So we've calculated out for every single data value the deviations from the mean. Now they all represent differences, and we like to find the average distance, difference, or deviation. But we can't just add up those deviations as they stand now. Perhaps you can see why. Some of them are negative and some of them are positive. It turns out that if we add up all the deviations from the mean, we'll get the number 0. And it won't make very good use for us to say that there was 0 deviation from the mean, because there obviously were deviations in all 8 data values. So we need to take care of the fact that our deviations have signs. And a way that we do that, after we've figured out how far each data value is from the mean, is we square those deviations. So for every single one of those deviations from the mean, after I've figured out how far a data value deviates from the mean, I'm going to square that difference. So the data value 30.1, that was 2.4 dollars below the mean. When I square that, I'll get positive 5.76. The data value of 32.7, that was 20 cents above the mean. When I square that, I'll get 0.04, or 4 cents. Now those are all positive, and so now I could add up all of those data values together. And that's exactly what we do when we figure out a standard deviation. Once we've figured out the deviations from the mean, we square those deviations and we add them all together, because after all, we're interested in finding an average. In this case, we find out that for Beth's 8 data values, the sum of the squared deviations is $35.34. But remember, we're interested in how far on average these deviations are. So we need to do a division here. Now, a special rule that we use when we're calculating the standard deviation for a sample, when we go to figure out the average deviation, we actually don't divide by 8 here, which is the size of the data set. This is a sample. And whenever we're computing what we call the sample standard deviation, the rule is that we divide the sum actually by 1 less than the sample size. And this is going to give us a measure that we call the variance of this variable. So if I divide 35.34 by 7, we'll get about 5.049. That quantity is referred to as the sample variance for this data variable. Now, that's the sample variance. Where does the sample standard deviation come from? That number that we were looking at earlier in our summary statistics. Well, the sample standard deviation, it turns out, is just the square root of the sample variance. After all, if you remember earlier, we weren't just adding up the deviations, we were adding up the squared deviations. So we kind of have to undo that operation. And that's what we'll do at the end. After we've added together and found the sum of the squared deviations, and then we've divided by 1 less than the sample size, we'll take a square root. The standard deviation, which here is indicated by the lowercase letter s. S stands for the sample standard deviation. And here it's the square root of 35.34 divided by 7. When we take the square root of 5.049, we're going to find that value that we saw on the previous slide, 2.247. And that number is the standard deviation of the variable. Remember what this is again. This number, 2.247, is a measure of how far on average our data values are from the mean of the data set, the sample standard deviation. So now we have 3 important measures of spread that we've taken a look at: the range, the interquartile range, and the standard deviation. One final topic that we want to talk about here from section 2.3 are things called Z-scores. Z-scores give us a way to describe how far a data value is from the mean of its variable by using the standard deviation as kind of a yardstick. We have the following definition. For any individual data value, we define its z-score to be z equal to data value minus mean divided by standard deviation. What this means is that the z-score of a data value is going to tell us how many standard deviations a data value is away from the mean. If the data value is larger than the mean, then the numerator of that fraction is going to be positive, and we're going to end up with a positive z-score. If the data value is less than the mean, then the numerator of that fraction will be negative, and we'll end up with a negative z-score. Let's take a look at a couple of examples. Suppose you had some variable that had a mean of 30 and a standard deviation of 8. Well, for that particular variable, we would say that the data value 50 has a z-score of positive 2.5, meaning it's 2.5 standard deviations above the mean. Where did that come from? Well, we took our data value 50 and we subtracted the mean from it. 50 minus 30 is 20. And 20 divided by the standard deviation of 8 is 2.5. So 50 has a z-score of positive 2.5. The data value 32 is also above the mean, but not nearly as far above the mean as 50 was, because 32 is only 2 above the mean of 30. Then the z-score is 2 divided by 8, or 1/4, or positive 0.25. Now here's a question for you to think about. Let's see if you can answer this. Suppose that we're talking about that same variable, the one with a mean of 30 and a standard deviation of 8. If a data value from this set had a z-score of negative 1.5, what must that data value have been? Think about that for a moment now. You know that your variable has a mean of 30 and a standard deviation of 8. If you have that variable with that mean and that standard deviation, and someone says that the z-score for a data value is negative 1.5, what must that data value have been to have had such a z-score? Do you think you have it? Let's check your answer. The answer is the data value must have been 18. Why? Well, a z-score of negative 1.5 means that the data value was 1.5 standard deviations below the mean. How big is 1.5 standard deviations? Well, if one standard deviation is 8, then 1.5 standard deviations is 1.5 times 8, or 12. So that means our data value must have been 12 below the mean, since this is a negative z-score. And what is 30 minus 12? It is 18. And you can check that if you substitute 18 into the z-score formula, you will indeed get a z-value of negative 1.5. So a z-score is a useful way of describing the position of a data value by using the mean and the standard deviation for that variable. I'm going to finish this show here with a little challenge to you for folks that are in my statistics class. And this is going to be an opportunity to earn some bonus points next week. Here is Beth's tip data set. Those were the 8 values in the data set. And here were those summary statistics. Remember that Beth had an average total amount of tips of $32.50 per day. And also remember that we had computed out that the sample standard deviation was 2.247, just about $2.25. Here is a question for you to try on your own. For this tip data set, what would be the z-scores corresponding to the data values of $30.40 and $36.80? For those 2 days with those tip amounts, what would be the z-scores corresponding to each of those two values? One of those tip values is quite a bit above the average, and the other one is a bit below the average. Can you find their z-scores by using the mean and the standard deviation? If you can, determine what they are and submit them next week in the appropriate place to earn 10 bonus points. I hope you found this video to be useful as we've looked at measures of spread and we've introduced the ideas of range, the idea of interquartile range using the quartiles of the data set, and also finally the notion of the standard deviation. Range, interquartile range, and standard deviation are all useful measures of spread for a data set that can be helpful for describing a variable.